So, as Arthur mentioned, I studied formal logic, and particularly in the 19th and 20th century. And at this period of time, or at least up until this period of time, logic had been seen as more or less a static science, where you just create rules about logic and what you would need to prove certain things, and you stick with those statements, and you call it a day. But at this point in time, there arose the concept of a calculus of propositions. And this was the idea, similar to the way in which we derive arithmetic formulae. For example, if we have, considering the quadratic formula was derived from other formula that we had established prior, and we had a series of rules by which we derived the quadratic formula. And similarly with logic, not only are we sticking with our logical rules, but we are rather deriving new logical rules kind of ad infinitum and creating a sort of logical system by which we're continually developing and sort of making progress in our system of logic. And once we're able to do that ad infinitum, we're also able to have the prospect of grounding all our mathematical statements in logic. And so not only talking about arithmetic in respect to the axioms that you might expect in grade school, but rather even something even more fundamental than that. And so we oftentimes think of mathematics as going forward. A lot of this work was trying to go backward in our mathematical process. And then the third is to do all of this very developmental work within the framework of never getting to the point at which we have contradictory formulas or incomplete systems. And so completeness is the idea that within a system, any true statement can be proven in that system. And that's something that we want, because we want to be able to prove everything in our system. And then consistency, we want to get to the point at which we never derive contradictory formulas within a given system. And so this is a classic page from Principia Mathematica, the source I've looked at. And we have this idea of, here's one formulation, here's the proof of that formulation, and it has a reference number that will possibly be referenced later on in new formulations. And so we're constantly deriving and developing this system essentially ad infinitum. And in fact, they had more work on their hands after 3 volumes of hundreds of pages of this. And then there's this very classic formula that we never want to negate. Essentially, we never want to have both P for any P and not P. And so it is always true that it is not the case that P and not P. Because if we have contradictory formulas, as we will see, we have problems. So the first system that we're going to be looking at is Peano arithmetic. He was one of the first players in trying to ground mathematical statements in logic, but he did it in a quite particular way, and in a very interesting way. His way was to establish a set of logical propositions that will kind of serve as our rules by which we derive new formulae, but then put in those formulae seemingly meaningless symbols that we will just put into these propositions and see what they hold. And the analogy here is when you're playing chess, you're not thinking about the fact that the literal piece itself is the substance of the game, but rather it is the sort of rules that we associate with that piece, and that's why we can replace any piece in our chessboard and have a perfectly functional game of chess afterwards. We're just throwing things within the rules by which we handle those objects. And what he will do is he's going to input arithmetical concepts, but kind of protected against any interpretation. And then confirm that when we combine all those terms with our logical propositions, that the conclusions will hold and are consistent. So, for example, these are a few of the logical propositions that he has from a set of 66 that he develops throughout the paper. For example, this first one is pretty obvious: A implies A. Or if A equals B and B implies C, then A implies C as well. So it's very simple things, but you can imagine that we can replace any logical statement for A and B, and it would still hold true. And then an explanation and axioms are taken to be these sort of meaningless symbols that we're throwing into the calculus. We're not trying to interpret these in any way. We're just trying to put them into the calculus and see what happens in the output. And then there's one definition in this paper, which is simply to define the signs of the natural numbers. So 2 equals 1 plus 1, 3 equals 2 plus 1. The only axiom that we have is 1 is a number. We have not established that 2, 3, 4, and so on are numbers as well. And so the natural next step is to show that 2 is a number. This is the statement 2 is a number, and we're going to go throughout the proof and prove that 2 is a number. I'm not going to get into the details specifically, but the point of this proof is that is the left-hand column. The left-hand column is essentially saying, let me replace the sign 1. Let me replace the sign 1 for A in proposition 6. And so I'm going to proposition 6. I'm looking at A, and I'm throwing in a symbol 1 and seeing what it yields in the output. And this is what it yields in the output. And so in that way, we are just putting our symbols into these systems and seeing that they do in fact yield a consistent system, and therefore we have 2 as a number. So following this, we have Alfred North Whitehead and Bertrand Russell, who wrote the book that I had showed on the first slide, Principia Mathematica. And Principia Mathematica propounded to ground all mathematics in all mathematics in logical axioms. And in this way, and differing from Peano, it wasn't rather to try to use logical propositions to reason about meaningless symbols, but rather to define those arithmetical concepts in relation to logic itself. And so mathematics is an extension of logic, not as opposed to we use logic as a tool to address mathematics, but logic is at the very basis of mathematics. And so from these primitive propositions, we are going to prove more logical propositions in this system of calculus, so that everything is grounded in these primitive propositions, and then extend those mathematical concepts from these logical propositions, and try to develop this in such a way that we have an entirely complete system of mathematics that can cover and prove any proposition that we could possibly come up with in our mathematics. And so I'm not going to get into the details of what these are specifically, but these are examples of where, as opposed to Peano, who just said, we're just going to call 1 a number, here 1 is defined as a very specific logical concept. And these are defined in the past about the way in which relations work with certain classes. But those are all logical concepts, and he's defining numbers in relation to logic itself. And if you notice, these are very high numbers, which means that he's had a lot of development coming into this. This is not like the first few pages. This is well into the work. And so an example of this, an example of kind of trying to ground kind of basic logical notions and even more primitive concepts is the fact that implication in Principia Mathematica is material. And this is to say that P implies Q we're going to kind of try to protect that against interpretation by just grounding it into an even more primitive logical notion, namely that it is equal to not P or Q. And I can, if you want to understand specifically why he defined it in that way, you can talk to me afterwards. But the more important point of this is that the very first primitive proposition that he states is what is commonly known as modus ponens, which is to say that anything implied by a true elementary proposition is also true itself. And this is kind of a simple way to say that, is that if we know for a fact that P implies Q, and we know for a fact that P is true, then Q also must be true as well. And this is going to be very important coming up. So one of the propositions that we have is that, and which is derivable from the primitive propositions, is that if P, then if not P, then Q. And the reason this is important is that we can use this to prove that, actually to establish that Principia Mathematica will not be founded on an inconsistent system, because everything is hinged on this type of proposition. Assume, for example, that there exists a system in which both some statement S and not S can be proved from the axioms. That is, we have two statements that are contradictory. We have an inconsistent system. Then S is true. But as we've established from the previous slide, if S is true, then if not S, then Q. But we've also established that not S is true. Therefore, Q must be true as well. And therefore, because of the indeterminateness of Q, we could, in theory, prove any statement Q from the fact that we have omitted both S and not S in our system. And so you can imagine all the possible propositions that you could possibly substitute for Q, but both true and false alike. But the point is that if we have an inconsistent system, then we necessarily can prove any proposition whatsoever in that system. And so that's the sort of importance of consistency, is that we want to be able to have a system in which we are only proving true propositions. Yes, any proposition can be proved, yes. So with that in mind, with that concept of consistency in mind, we're going to move on to Kurt Gödel. And I tried to find the most sinister looking photo of Gödel I could find. And what Gödel worked in primarily was metamathematics. And metamathematics is kind of what we've been talking about up until this point, which is essentially the idea of the way in which some propositions are proved within certain systems. Not about what that proof necessarily is, but asking the question, considering some proposition, is it possible to prove this proposition within some certain system? And particularly what he showed, and which I'm going to outline the proof of, is that in some system robust enough, such as Principia Mathematica, that propounds to envelop all of mathematics and ground it in its primitive propositions, there always arises some propositions that are undecidable in that system. There are propositions that neither their affirmation nor their negation is provable within the system. They might be true and they might be false, but there's no proof that will arrive me at that conclusion. And the way he did this was to show that any formula within Principia Mathematica can essentially be encoded in some number, and particularly some unique number. And because Principia Mathematica talks about numbers and reasons about numbers, it essentially can reason about itself. It can output, we can encode some formula into some number, and then we can plug that number back into the formula itself, essentially. He exploits this sort of self-referentiality and shows that certain types of those types of formulations are unprovable in the system. And so his methodology of this was to take each symbol of a formula, such as all these symbols, and encode them in some natural number. And then from those natural numbers, we have a unique sequence of symbols for any formulation. This formulation so happens to say that there exists some x such that x is the next number after y. And so we can actually encode each of those symbols into their correlative symbols, and then use a sequence of prime numbers and use the code as the exponent of each of those prime numbers. So we associate one number n as the product of all the prime numbers with exponents correlative with the sequence of codes in the formulation. And because of the fundamental theorem of arithmetic, this number n is unique for this sequence of symbols. And in fact, I wrote a program that actually encodes some sequence of symbols into its number, and also takes that number and encodes it back into its formulation. But also these are very big numbers because of these, multiplying all these prime numbers with these massive exponents. And then even not only for single formula, but also for sequence of formulae, I can encode unique numbers for those formulae. So if I have a formula with number n and a formula with number m, I can say that the number associated with that sequence of formulae is equal to 2 to the n times 3 to the m. And so a consequence of this is that perhaps I wanted to know if the f sub n is the antecedent of my formula or my proof. I could just divide the number I could divide this number by the number that I'm wondering if it's the antecedent or not. And if it's divisible, then it is the antecedent of my proof. And essentially, and that way I can get answers to my questions about proofs by reasoning about the arithmetical relations between those, between the numbers of the formulae in that proof. And essentially what Gödel was trying to do is boil metamathematical statements down into mathematical statements about those, metamathematical statements about propositions into mathematical statements about natural numbers. And this is the idea that we're going to feed that natural number back into the system that addresses natural numbers. And so the kind of the finality of this proof is to define a class sign, which is to say it's just a formula within Principia Mathematica with only one free variable. So for example, x is prime would be a class sign because it's just taking in one free variable x and asking if it's prime or not. The other one was there exists a x such that x is the successor of y, is also a class sign. Except it's only determinate when x is determinate, because x is prime doesn't mean anything. 2 is prime or 16 is prime is determinate because it's actually yielding some logical answer to my question. And then because, as I've shown, these class signs can be encoded in unique numbers, I can essentially order them in some sequence of their Gödel number, and then I can ask the nth class sign is going to be notated R of n. And then this is a little bit tricky. I can say that the formula of some class sign, because a class sign is a formula containing one free variable, some number, I can input that formula I can input the Gödel number associated with that formula back into the free variable itself. So for example, x's prime has its own Gödel number. I can input that number and ask if it's prime or not. It might be, it might not be. But that's what that bracket R of n with n. I'm not going to call it R of n with n. And now this is kind of the trick that Gödel does is he makes a class of numbers n and k such that R of n with n is unprovable. Now, because as we've established, metamathematical concepts such as can't be proved can be addressed in mathematical terms. Because they are addressed in mathematical terms, they can be contained in the system Principia Mathematica itself. That is, and because they are in the system of Principia Mathematica itself, they can have their own class sign. That is, there's some class sign S such that S with n states that n belongs in K. Because this is a concept that can be boiled down to some class sign within Principia Mathematica. And essentially, with this, and because it's a class sign, there exists some Q such that R of Q equals S. That is, S equals some class sign in this order of Gödel numbers. Q is the Gödel number of S. And this essentially does is that it says that R of Q with Q asserts its own unprovability. And so with this reference on top, we can ask a question. So we make the statement, both R of Q with Q and not R of Q with Q are not provable within the context of Principia Mathematica. We don't want this to be true, because if it were not true, then we have, if it were not true, then we have an undecidable proposition within Principia Mathematica. But the whole point of Principia Mathematica was to create a complete system by which we can prove everything within the system we have. Suppose R of Q, so we're just going to try to negate this. We're going to try to suppose the opposite. Suppose that R of Q with Q is provable. Well, if R of Q with Q is provable, then that is the same as saying that Q is in K, because that's how we're defining R of Q with Q. But if Q is in K, then R of Q with Q is not provable, as we're defining the class K. So now we have arrived at a contradiction. Suppose then that not R of Q with Q is provable. Then, because of the way in which we're defining the class K, Q is not in Q. Q is not in K, and therefore R of Q with Q is provable. Now we have not R of Q with Q is provable, and R of Q with Q is provable. Therefore, we have an inconsistent system. But we're assuming that Principia Mathematica is consistent, and therefore we have a contradiction. Therefore, assuming that Principia Mathematica, G must be true, that is, both a statement's affirmation and negation are unprovable within the system itself. What Gödel calls that is an undecidable proposition. That for a system that is robust enough to talk about natural numbers, there inevitably rises statements that are both their affirmation and negation are unprovable within that system. Now, just as a caveat to this, one of the proofs that Gödel had early on was, or actually as his doctoral thesis, was the completeness theorem, and he actually indeed proved that within logic, any true proposition can be proved. He didn't specify within what logical system or axiomatic system, but he said that if a statement is true, it is indeed true that you can prove that proposition. It may be in an axiomatic system that we haven't even seen yet, that we need to develop more and more. And it may be that within the system that we're working in right now, it is unprovable. And so I think it's important to recognize that, because as these M.C. Escher illustrations show, and actually Douglas Hofstadter in his book Gödel, Escher, Bach, uses these as kind of analogs to what Gödel is showing in his incompleteness theorem, kind of showing, especially with this waterfall one, especially showing how a system kind of wraps back in on itself and creates a closed system. And necessarily there exists kind of like a space around it that it cannot reach, because it is a closed system. It has wrapped back in on itself. What Gödel's incompleteness theorem shows is that we always are at a liability to try to expand the system, to kind of break the circle of this endless loop. But what Gödel's completeness theorem shows is that there is a possible axiomatic system by which we can prove any true system. So the point is not to just give up on logic altogether because they're undecidable propositions, but rather to work harder to think outside the box of this closed system to create new axiomatic tools by which we can progress in mathematics.